Hello, everyone. My name is Carlo Giacometti. I am one of the developers for the audio-related functionality for Mathematica. And today I'll be talking about the new features that we introduced in version 12 that bridge audio and signal processing and machine learning. So in the last version, we have added several very high-level built-in functions for audio identification, speech recognition, and pitch recognition. These are high-level super functions that rely on neural networks. The other very important part that was added was a very efficient integration between audio processing and signal processing, and the machine learning and the neural net frameworks. I will give examples of these later. And of course, you'll have easy access to pre-trained models using the Wolfram neural net repository. So as I said, the main bullet points that we have for this is speech recognition, pitch recognition, audio identification, of course, audio processing and analysis capabilities. And as I was saying, we have support for audio in all our machine learning function, as well as neural networks. And of course, there are several corollary things that come with support for audio in neural networks. So I will just quick show you the organization of this product page. You can see the first row contains examples from very high-level built-in functions to perform recognitions of both speech and pitch. The second row is instead focused on audio identification. So, for example, just identification of sounds, specific sounds, some time-resolved identification, and then a more advanced user-defined classification using the audio identification features. The third row is exclusively about feature extraction. In this case, mostly semantic feature extraction, which is a crucial step in understanding the contents of an audio signal. The fourth row is exclusively about classification of audio signals, both using out-of-box machine learning functionality or neural networks from scratch. And the last row introduces the crucial element that allows a programmer to bridge audio signals and neural networks, which are the net encoders, which take audio objects and transform the content of the audio object into a format that is more friendly to a neural net. So my plan is to show you some examples in the page and some examples actually in a notebook, just because since we do have this very nice dynamic interface, why not use it? So I'll show you the first one in a notebook. So first, I synthesize a very simple speech signal.
Hello, I am the computer.
And as I said, in version 12, we have introduced this speech recognize function that, as advertised, very simply performs the speech recognition of a signal. This obviously uses a neural net as the basis for its operation. And the nice thing about it is that you can access the pre-trained net using the net repository. This is the Deep Speech 2 network trained by Baidu. And as you can see, it's pretty straightforward network with a convolutional front end and then a recurrent network heart of the operation here. So we can just take this net and apply it to our signal. and you can see the result is a list of characters. And we can join the characters to get the result. So you might ask, well, if I can use this, why would I use the speech recognize function? Well, the speech recognize function, in addition to the decoding that is done by the acoustic model, which is this network, also runs the output through a language model to potentially correct spelling mistakes. So this decoding is obtained using a CTC decoder. The input to the CTC decoder is a list of probabilities per each time step for every letter. And we can easily compute that by killing the decoder into our network. And we can visualize these probabilities. As you can see, if you look at the time plot of this, you can see how this then gets mapped onto the decoder string. So another potential application of the speech recognize function is to build an audio-based question answering system. In this case, we will just look at a simple paragraph of text that has some information, and we can have a question that is then transformed, that is recorded, is then transformed into text. Now we can add another neural network building block with find textual answer. This function essentially takes a question and a context and tries to find the answer to a question into the context. In this case, you can see that the output is just the original context with the relevant answer highlighted. And we can use speech synthesize to convert the result into an audio object again. So we have started with a question in an audio object, and we have finished with a reply, an answer, in another audio object. Another high-level function that has been introduced in version 12 is pitch recognize. So let's take a simple recording, in this case, of a piano, just 3 notes. We can use pitch recognize to figure out the pitch of the original signal. We can, and pitch recognize exposes a method option through which you could actually select a method that is completely neural network based. This method is based on the creep network, which is also available from the Wolfram neural net repository. So we can, again, download our network, which was trained to predict an estimate of the pitch as a probability distribution on a set of 360 pitch classes. Now we get a sequence of these probability distributions, and we need to decode this into a single estimate. So there is some machinery that needs to be defined, in this case, a hidden market process to interpret the sequence of states and to output a single prediction. And I can easily apply this function onto my audio signal. You can see that I get a time series with the recognized pitch and another time series with the confidence of this prediction per each time step. And we can easily plot, as you can see, the frequency, and you can see where the frequency is plotted in red, then the estimate is definitely not confident. And obviously, it's located in places where there is silence. So let's move on to the second row, where the main topic is audio identification. So first of all, let's talk about the top-level function that has been introduced in version 12. Audio identify. This function uses a deep neural network to identify the sound sources in an audio recording. The ontology that has been used for the training contains more than 600 classes of sounds. So let's start with the recording of an acoustic guitar. And audio identify very luckily and outputs the correct result. Now, we can do the same kind of identification using all of our example data collection. And you can see how most things are recognized in a reasonable way. You can see that there are multiple results per each of the signals. These are the the most probable results that could happen at the same time in a signal. In a similar fashion, we can restrict the recognition of a signal onto a specific category. In this case, I have a collection of sounds from cows, birds, and cats downloaded by Freesound using the web audio search function, which also was introduced in version 12. So we can simply use audio identify on each of these signals while restricting the result to the specific category of sounds produced by animals, and produce a workflow out of it. And you can see how the main results actually fit with the type of animal that is supposed to be in the recording. Another interesting thing is, since we have support for audio signal in the machine learning function, and this support comes through semantic feature extraction, we can simply say feature space plot of our audio signals. And as you can see, they are kind of clustered into their own categories automatically. Here, there is no user input. This is just the audio objects that go into the feature space plot function. And they are separated in the feature space because semantic features are automatically extracted from the signals. The last example I want to show you about audio identification is how to classify instruments using audio identify features. So as I said before, since we do have support for audio in all of the machine learning functions, and this relies on a variation of the net that was used in audio identify. So essentially the net for classification is chopped off, and that becomes a very powerful semantic feature extractor. So what classify, for example, needs to do once it is given audio objects as an input is just classify a bunch of vectors of numbers. And that is something that classify does really well. So we can, in this example, collect a bunch of signals from different instruments. And in this case, I chose acoustic guitars, drums, and trumpets, again, using web audio search. And I will not run this example right here. It takes about 1 minute. I can just call classify on my training data, and you can see the information. It will immediately get to a 94% accuracy. Of course, this is on the training set. If I use classifier measurements, I will get the accuracy on the test set which is still a very respectable 87%. And keep in mind, again, that there is no user input. I haven't defined a neural network. I haven't given classify additional information. This is just classify run on 90 examples of audio signals. So that is pretty convenient that complex processes like this are so simplified for the user. The next row deals with feature extraction. Again, this is an extremely important part of our integration between audio neural nets because we want to make simple the extraction of semantically valid, semantically sound features. So what is feature extraction? The idea is you take a complex object. It could be text, it could be audio, it could be an image, it could be a graph, and you want to convert this complex object into a vector of numeric values, which is, again, what computers understand best. In this case, I will just take our collection of example data. Again, I will use feature space plot to display all of these signals in a semantically significant 2D feature space. And you can see how things are clustered in a sensible way. All of the impulse responses are clustered together right here. You get human-related sounds up here. You can get, for example, more human-related sounds here. All of instruments are relegated in this area. Similar instruments are almost overlapping. So you can see that there is some understanding of the content of the signals. Another thing that you can do with feature extractor and the machine learning functionality is define a feature nearest function. So this is essentially a function that takes a bunch of data, extracts the features for them, and whenever you give it a new signal as an input, it will tell you which of the original signals is the closest in the feature space. In this case, I have a new recording of a dog bark. And if I ask it what the closest recording is, I will get, again, the original recording of the dog bark. In the same fashion, you can build a feature extractor function using feature extraction. This will extract the optimal features from the example data that you have here, and will produce a function that will reproducibly extract a feature vector from arbitrary input data. And in this case, since the dimensionality of the extracted feature is only 38, we can get a very simple unique visualization for our signals. It is also possible to extract a specific feature. We can use something that is used in classic signal processing, for example, the Mel frequency substar coefficients, or we can join together feature extractors, in this case, the MFCC and the numeric vector feature extractor, to create custom ones. And here we go. The other option to extract features in a more user-controlled way is to extract features using a neural network. So, as I was mentioning before, the machine learning functions in the backend use a modified version of the audio identify net. this can be done by users as well. If I download the audio identify net from the repository, I can easily extract parts of it. In this case, the part that is mapped on each of the chunks of the signal, and I can modify this long network by taking out the last few layers that are in charge of the classification, and I am left with something that extracts a fixed size, semantically meaningful vector for each input. And here it is, as you can see, the input is my audio object, and the output is a vector of about 1,000 elements. You can apply this feature extractor to an audio object. Again, the output visualized like this is kind of useless. It's just a bunch of numbers. But if you use this, for example, as feature extractor in a function like feature space plot, now this might take a little bit, you can see that you get something that is similar to what we obtained in our previous example here. Again, these are embedded in a semantically meaningful way. And you can use, in a similar way, another pre-trained feature extractor from the neural net repository, in this case, the VGG-ish feature extractor trained on YouTube data. So the next row deals exclusively with audio classification. Audio classification can be done in several ways. So first of all, I'll show a very simple example of classification from scratch. So in this example, the dataset that I will use is the spoken digits commands from the data repository. This is a pretty simple dataset. It contains audio objects that are recordings of digits from 0 to 9.
8.
By a lot of different speakers. So first of all, you need to decide what kind of, what will be the bridge between your audio object and your neural network. In this example, we will use the MELF frequency substyle coefficients, which hopefully will reduce the dimensionality of the signal, but at the same time preserve the important information for the understanding. This is just some example of what the result of the net encoder is. The net is just a bunch of gated recurrent layers, and then a classification stack that is done by using linear layers. The training will be left completely on its own. You can see I am not really giving any specific hyperparameters to net train. The inputs are simply the network and the training data. The only option that is specified is the validation set, which is defined to be as a random subsection of whose length is 5% of the length of the original dataset. And as you can see, this converges in 40 seconds or so. And you can inspect the results using net measurements. The accuracy is 94%, which is pretty high. One interesting thing that can be done after, so again, here we have created a classification net. The classification accuracy is 94%. Now we can take the same net and do a similar operation to what we've done for the feature extraction example. We can discard the classification stack and just use, just the output will not be a number, will be a vector of size 10. So we can even actually, maybe this will This will produce a vector of size 64, which will semantically represent the input, given the space that we have used as our training examples. So we can use feature space plot using the feature extractor that we have just trained to visualize the test data set. Let's see, this one might take a little while, just because, and here we go. Here we have signals that are semantically clustered by their content. The next example that I'll show is classification on a more established data set. So the data set that I will be looking at is the ESC50 environmental sound classification data set. It's about 2,000 sounds grouped into 50 categories. You can see the state-of-the-art accuracy results. These are a bit outdated. I guess the repository has not been updated in a while, but you can get the order of magnitude of what a good result on this dataset is. In this case, I can import, I already downloaded the dataset, I can import the metadata. It looks roughly like this. You have a file name and a category are the important information. I can subdivide into a training dataset and into a testing dataset. And in this case, and again, I will not run this example. This takes a couple to 5 minutes, if I'm not mistaken. In this case, I just do classify on our training dataset without providing any additional information. I'm not defining any custom network. And you can see already with no user input, I get an accuracy of about 90%. Another approach to do classification is transfer learning. So what is transfer learning? Many times you have too little data to train a network. So instead of training a network from scratch, you might want to use a pre-trained network that was trained on a similar, not the same problem, but a similar problem. And you can make the assumption that the features for the problem that the network was trained for are still relevant for your task, the task that you have at hand. So you use essentially the network as feature extraction, feature extractor, but then you train a classifier on these extracted features. We are using the same dataset here. We have the same features. We can define our feature extractor in the same way as we did before. We can define our classifier network just by using a bunch of fully connected layers. And then the only thing that we need to do is train this classifier. Again, this is pretty quick because I am just training a bunch of fully connected layers onto a bunch of vectors. And we get the final net by joining the feature extractor and the classifier that we just trained. And we can compute the accuracy of the result. So this might take slightly more than I expected. Okay, 89%. This is slightly disappointing, given that with the no user input, we got such a high result. But there is some non-deterministic bit in our training, given that we used a dropout layer. One strategy to increase this accuracy, for example, would be to train an ensemble of classifiers and then average them out to get higher accuracy. Another interesting example that uses classification is how to train a sound event detection net without having data that is labeled for sound event detection. What is sound event detection? The idea is pretty simple. You have a signal, and you want to know where in the signal a specific event happens. In our case, though, we only have access to weakly labeled data. Our dataset, the dataset that we'll use is a very simple one. It has a bunch of recordings of cats and of dogs. And the format is very simple. You'll have a recording and label that will tell you if that recording is of a cat or of a dog. But there is no information in the dataset on when this event happens in the signal. So we can easily get our dataset from the data repository. This is a random sample of it. Pretty straightforward. Again, recording where only either a cat or dog is present and label that exemplifies what is the content of the signal. We can inspect the duration of all of these signals. Oops, this might take a bit more than... Yeah, okay, let's close this and see what happens. Okay, this is not really what was supposed to happen. The point, I am not exactly sure what happened here. The point is that the duration of the recordings varies between 1 and 18 seconds. So we can easily split the data set into a training and a testing parts of the data set. We can inspect the total duration of the training and testing data set. And now we need to figure out exactly how to feed this data into our neural net. In this example, we chose the MEL spectrogram. One additional thing that is very important in this dataset is that our net encoder will also need to perform some kind of data augmentation to make the training more effective, because our data set is pretty small. So in this case, the input will be randomly shifted, and some vocal tract length perturbation will be applied. The net is pretty similar to what we had before. It is a stack of, whoops, sorry. Let me just reevaluate our classes here. A stack of gated recurrent layers, sorry. Let me redefine this very quickly. Again, the network is very similar to the one that we previously used, a bunch of gated recurrent layers. But now the classification is done in a way that is a bit subtly different. Before, we were just... so you can see the gated recurrent layer outputs varying length output. Now we need to get this to a fixed length and then classify the result. Before, we would just take the last element of this sequence and classify the result. In this case, we just aggregate the sequence over the time dimension using a max function, and then use that as our probability distribution. I will not run the training now. Well, I guess I could. This just takes about 1 minute, evidently. Here we go. Again, the data set is pretty small, so I am not really expecting to get a stellar classification result. But the point is, I want to be able to transfer a classification network into a sound event detection network. And for that, this trick of using an aggregation layer instead of a sequence last layer is crucial. Because if I then take out my aggregation layer and map a softmax layer on my sequence, the output of the network will then be able to be interpreted as a sequence of probability distributions. And here we go, the training supposedly is finished. Here I am just doing something that is just some kind of plumbing. I am taking out the augmentation of the net encoder, and I can look the classification results again. I was not expecting super good accuracy, but still 94% is, I will not complain about this result. As I was saying, what we want to do is remove the aggregation layer and reattach the softmax layer after it. This will output us a network that returns a sequence of class probabilities instead of a single classification result. So again, some plumbing to take the output of this network and transform it into a couple of time series. And now we can look at how this works and if the result is actually reasonable. I am just here constructing a test signal by joining random cat and dog recordings one after the other. Here we go. So we have a signal that's 30 seconds in length that contains both cats and dogs sequentially. So what we can do is plot the result of our time resolved network. You can see, well, here at the bottom are the labels that we know are the ground truth, because this is how we constructed the signal. And in blue, we have the probability of the signal belonging to a dog, and in yellow, the probability of the signal belonging to a cat. And as you can see, the two things line up pretty well in a time-resolved fashion, even though we never taught the network how to localize these events. Again, some more plumbing to visualize the intervals. And we can simply visualize the intervals that belong to cats or dogs in a single plot, highlighting the waveform of the signal. So the last row I will show you on the web page. Last but definitely not least, as I was mentioning before, the net encoders are the entry point for audio objects into the neural network. They transform a complex object into a vector or a sequence of vectors. The audio signals are complex entities. They can be very long. For example, the most common sampling rate is 100,000 hertz. So per each second, you get about 34,000 values. The longer the input is, the more humongous this becomes. So you do need ways of transforming this into a format that is more friendly to neural networks. And we do have several audio-related encoders. The first one just outputs the data. All of the other ones are based on the short-time Fourier transform. The idea is you partition your signal into potentially overlapping partitions, and you apply a Fourier transform on each of the partitions. And this will give you both time and frequency information. And instead of having a sequence of a million values, you'll have a matrix of slightly more approachable dimensions. And there are several variations. You have the full short-time Fourier transform, which gives you both real and imaginary information per each of the Fourier transforms. The spectrogram, which just gives you the power spectrum, so the imaginary part is discarded. Well, the phase is discarded, sorry. The MEL spectrogram, which returns a spectrogram that has been filtered in a way that kind of mimics human perception of pitch. This also performs some kind of dimensionality reduction. And finally, the MFCC, the MEL frequency substar coefficient, that does some further dimensionality reduction onto the MEL spectrogram, and still preserves a lot of the information contained in the signal. The other thing that I showed in this last example already is the data augmentation. Again, if your data set is pretty small, this exposes the network to a bigger variety of signals. And there are several augmentations that are available: time shifting, volume variation, noise addition, convolution to simulate different reverberant environments, and vocal tract length perturbation, which is very useful on speech signals. Super important thing, these net encoders for audio are very efficient. You can see the dramatic speed up that you get. For example, by computing the spectrogram with a net encoder versus using the spectrogram function. You can see as a function of that set size, you get speed ups up to 300%, 300 times. You even get a speed up by comparing the net encoder with parallel map and spectrum array. And this is even more pronounced if your data is saved as a collection of audio files on your hard drive rather than a bunch of audio objects that are stored in memory. We do have, as I said, these presets, but it is pretty easy to build a custom audio encoder by using the function net encoders and using as an input simpler building blocks like the audio net encoder or the audio spectrogram net encoder. In this example, I compute a spectrogram, but to each of the frames of the spectrogram, I subtract a mean value and divide it by the standard deviation. So essentially, this is a normalized, frame by frame normalized spectrogram. And yeah, that is all I wanted to share for today. Hope you enjoyed both this talk, and you will enjoy in the future playing with audio signals and machine learning and neural networks. Thank you.